shear force and bending moment. Shear force and bending moment. Alright. Shear force and bending moment is an aspect under strength of material. Right? So let's discuss shear force and bending moment, as I said. Alright, first things first, for us to start discussing about how to draw shear force and bending moment diagram, we need to know some basic terminologies, right? Some terminologies when it comes to drawing shear force and bending moment. So let's start with the basic terminologies. It involves a shear force and bending moment. Number one, beam. Beam. Let's start with beam. Beam. Beam is one of the terminologies in shear force and bending moment. Alright, let's discuss beam. What's a beam? Hold on. A beam is a structural member that is designed. A beam is simply a what? A structural member that is designed to resist a load acting at right angle. Or you can say a beam is a structural member that is acted upon load at right angle. Right? So a beam is simply a structural member that is acted upon loads at right angle. Loads at right angle. Right? So when it comes to beam, we just define beam. Let's move to the type of beam we have. Type of beam. Alright. Type of beam. Types of beam. Number one, we have statically determinate beam. We have the statically determinate beam, and we have the statically indeterminate beam. Alright, these are the two types of beam we have. Type of beam, number one, statically determinate beam, and number two, statically indeterminate beam. Let's discuss the first one called statically determinate beam. Statically determinate beam. Alright, statically determinate beam. These are beam whose reaction can be determined. Statically determinate beam. These are beam whose reaction can be determined using the equation of static equilibrium. I said statically determinate beam. These are beam whose reaction can be determined using the equation of static equilibrium. That's the definition for statically determinate beam. Example of such beam are, number one, example of statically determinate beam. Example of statically determinate beam. Number one, we have the simply supported beam. Number two, we have what? Simply supported beam. Right? Let's explain this. Simply supported beam. This is a beam whose ends rest on support. Statically determinate beam, simple supported beam are beam whose ends, these ends rest shown below, right? So this, if you see a beam in this format, it's called what? It's called what? A simple supported beam. Under what? Statically determinate beam. Alright, the second example when it comes to statically determinate beam is called the it's called the overhanging beam. Overhanging beam, right? Overhanging beam. Overhanging beam is simply a beam. Overhanging beam is simply a beam which its two ends do not rest on support. Overhanging beam is a beam which its two ends do not rest on support. Overhanging beam is a beam whose two heads do not rest on support. See, these are supports, but the support are not at the two ends. So the two ends do not have what? Support. In this case, we call it what? An overhanging beam. Alright, what of this? What can I call this beam? If I have something of this nature, observe the support here and the support here. I have this one, I have this. What can I call this? It's still what? Overhanging. Right? When a beam does not have support at its two ends, it's called overhanging. Another way to know it is that when a beam is extended this way, such that there is no support at the end here, it's still called what? It's still what? An overhanging beam. Right? A overhanging beam per se. Right? So let's move to the third one. The third example, number 3. We have the first one, simply supported beam. Number 2, overhanging beam, right? And number 3, cantilever beam. The third example is called cantilever beam. Cantilever beam. Alright. Cantilever beam is a beam. Cantilever beam is a beam that has a side fixed while the other free. Cantilever beam is a beam that has one of the side of the beam fixed while the other free. Cantilever beam is a beam that has one of the side fixed and the other free of support. Right? So these are like 3 examples when it comes to statically determinate beam. Let's discuss statically indeterminate beam. Number 2, statically indeterminate beam. Statically indeterminate beam, by definition, hold on. Statically indeterminate beam are those beams whose reaction cannot be determined using the condition of equilibrium or using the equation of static equilibrium. I said statically indeterminate beam, these are beams whose reaction cannot be determined using the equation of static equilibrium. Example. Number 1, we have continuous beam. Continuous beam. Number one, continuous beam. Continuous beam is simply a beam. Continuous beam is simply a beam that has more than two support systems. Continuous beam is simply a beam that has more than two support systems. Right? It has more than what? Two support systems, as you can see in front of you. Right? So I have this. This is what? A continuous beam. A beam that has 3, 4, 5 support systems is called what? A continuous beam. Have this. Alright, the second one is called fixed beam. Fixed beam. Fixed beam. A fixed beam is simply a beam that has its two ends, that has its two ends fixed. Hence, right? Hence, this end and this end here, they are fixed. For this one, let diagram below. A fixed beam is simply a beam that has each two heads fixed. Now this is fixed. So this is the diagram for a fixed beam per se. So this is like I want you to know when it comes to beam, you need to know the definition of a beam. Next up, the type of beam that we have. These are like the type of beam we have. Let's move to the second terminology. We said beam is the what? First terminology. Alright, let's move to the second terminology called load. Second terminology called load. Let's call load. What is load by definition? A load is simply a force that acts on a body. A load is simply a force that acts on a body. Alternatively, I can define load as saying a load is a force that acts on a structural member, usually at right angle. I said, alternatively, we can define load as what? The force that acts on a structural member, usually at right angle. So that's like the definition for load. Let us call the type of load that we have. Type of load. Types of load. Type of load. Number one. Type of load. Number one, we have called the point load. Point load, or you call it what? Concentrated load. Type of load. Number one, point load or concentrated load. Number two, we have it called distributed load. Alright, these are like the types that we have. Number one, point load or concentrated load. Number two, distributed load. These are the type of load that we have when it comes to structural mechanics. Alright, let's go to the first one called point load. Alright, definition. A point load or concentrated load are loads that act at a point. That's all. Point load. Load at a point. So, point load is simply a load per se or a force that acts at a point. Point load are load or force per se that acts at a point. So we said point load is a load that acts at a point. Point, load, load, point, right? So as a load that would act at a point. So I have this for that man. The second one, we call it what? Distributed load, right? Distributed load is simply a load that is what? That is spread through a distance. Distributed load is simply a load that is spread through a what? A distance. Alright, for when it comes to this man here, we have two cases. The case one is that we have what we called or per se, let's say distributed load is categorized into two. Number one for it, number one is that we have what we called the uniformly distributed load, which is illustrated in this form. Now, whenever you see a load in this format, it's called uniformly distributed load, right? A load in this pattern is called a uniformly distributed load, or in this format, it's still called a uniformly distributed load. And also, the second one that we have is called uniformly varying load. Varying load, uniformly varying load, which can be illustrated from this diagram here. Alright, we said what? We have two types of distributed load. Number one, uniformly distributed load, which is in this format. Next up, uniformly varying load. For uniformly varying load, there are different types, right? So we have the triangular load. When it comes to uniformly distributed load, it can be in three forms. Number one is triangular load. Number two is trapezoidal load. Number three is parabolic load. When it comes to the first one I mentioned now, AII, you have what? The triangular load. I said when it comes to uniformly varying load, it comes in three dimensions, in three forms. Number one is what? Triangular load. How does this look like? I have something of this nature. Triangular load in this form, right? A triangular load. A triangular load. Have this. So this is what we call a triangular load. Is what? It is also called a uniformly varying load, right? This is called uniformly varying load. But what? Under what? Triangular load. Another one that we have is called trapezoidal load. Trapezoidal load. How does it look like? Something of this nature. Have this. This is called a trapezoidal load, right? A trapezoidal load, right? And finally, we have parabolic load, which can be illustrated as you can see support, right? Support. Alright, for this concept here, support, I will actually drop the link for more understanding of this concept, support. Check the description of this video. I will drop a link that will explain the real detail for what we call support, right? So when it comes to, for teaching sake, when it comes to support, there are about 3 types of support. Number 1, we have the pin support system, which can be illustrated in this format. This is called what? The pin support. Number 2, we have the ruler support. Right, which is in this form. And finally, we have fixed support. Finally, we have fixed support. Finally, we have the fixed support. Let's say I have 3 fixed support. How does it look like? This is what? A fixed support. I have this. These are like the 3 types of support that we have when it comes to support system, right? So note that for pin support, we also call it hinge support. We also call this knife edge support, right? When it comes to pin support only produces what? Just what? Only produces what? 2 reactions. Pin support produces the horizontal reaction and the what? Vertical reaction. You should know this from the concept of the year 1. That was strength of central magnets. Yes, you should know this. Next up, ruler support has what? Just a vertical reaction. Why this has what? Both horizontal and vertical, included with what? Moment. You should not take note of this. A pin support. We said pin support has what? Possess 2 reaction, horizontal and what? Vertical. Next up, ruler support produces what? Just what? A reaction. While pin support produces what? Horizontal and vertical with what? Moment. So we said the first analogy is what? Pin. Second is what? Load. Third is what? Support. Right here. Right? Right here. Alright, let's discuss one more concept. Where we can start drawing shear force and bend moment diagram. Let's go on concept. Let's discuss the condition of static equilibrium. The condition of static equilibrium. Put down. Number 1. The sum of the horizontal components must be equal to 0, or perhaps summation of the horizontal components must be equal to 0. Number 1, summation of the horizontal components must what? Be equal to 0. That's the first condition of static equilibrium. Next up, the second condition says that the summation of the vertical components must be equal to 0. The first one says the summation of the horizontal components must be 0. The second one says summation of vertical components must be what? 0. Finally, moment 3. Moment at any point should be equal to 0. We are saying that moment at any point P should be what? 0. Should be what? 0. These are like the what? The 3 conditions of static equilibrium, right? So let's start with sample problem 1. bending moment diagram of the figure as shown below. Draw the shear force and bending moment diagram of the figure as shown below. This is what? This is a point load. This beam is called what? A simply supported beam. Why? Its two ends are resting on support. Just follow this now. Next up, this is what? A pin support or in support. This is what? A ruler support or knife edge support. So now this is the simplest question you can ever see when it comes to shear force and bending moment. For this now, the first step is quite simple to solve this. We are asked to draw what? We should draw the shear force and bending moment diagram of this figure. First, how do you solve this? Your first step is to what? Draw the what? Free body diagram. By definition, a free body diagram is simply a diagram or sketch that shows all the forces that act on the body. That's all. So, for my figure diagram, for this figure can be sketched as I have my beam this way. We said pin support. If you recall when we said pin support, for this how many reaction? Just what? 2 reaction. That's what? Okay, listen please. Let's call this point A, call here point B, and call here point C. Alright, for my point A, I have what? 2 reaction, which is what? The vertical reaction and the what? Horizontal reaction. For my point A, this is point A. For my point B here, a ruler support has what? Just a vertical reaction. I have this. A vertical reaction for my point B here. And my point C has a pin support of, a point load of what? 20 kN. I have that from here to here is 5, here to here is 5. 5 meter, 5 meter. Listen please. This is A. This is what? A vertical sense and horizontal sense, right? Let me call it RAY, that is reaction at A on the what? Y-axis. Let me call it RAX, that is reaction at A on what? X-axis. What like all this be? This will be what? The reaction at B on Y-axis. Reaction at B on what? Y-axis. So this is like what we call the figure diagram. It shows you all the external forces that act on a body, right? So what is this? To draw the shear force and bending moment diagram for this figure, your first step is what? You need to know your RA and RB. So let's get RA and RB using the condition of static equilibrium. What's the first condition of static equilibrium? Number 1, we said summation of horizontal components must be what? Equal to 0. So consider the right force to be what? Positive, and left force to be what? Negative. From this body here, listen please. From this body, obviously, we said the first condition of what? Summation of what? Horizontal component. Which force from this body now? Which force is in this direction? Either facing here or here. Lying down. I can only see just one force, which is what? RAX. Right? So it's only RAX that I'm seeing that is in form of what? Horizontal. So now RAX is facing what? This direction. And this direction here is what? Positive. So how what? RAX. That's only what? The horizontal component I'm seeing here. That's all. Then what? Equal to 0. That's all. So in most cases, when it comes to functional mechanics, you are advised For pain support, you are advised to what? Put what? To the action. I just said. But when it comes to strength of material, we always what? Ignore RAS. Why? Because we know that at last, at the end, it will what? End up at 0. So in our next example now, I will not put this one here again because I know that it will what? End at 0. So hence, in that case, I will not consider the first condition of equilibrium. But for now, we're just starting. So let's do the normal procedure. Alright? So that's the first condition. Second condition, as we said now, was what? Summation of what? Vertical components. Summation of vertical components to be equal to 0. For this case here, consider two things, please. Alright. The first condition was what? Summation of what? Horizontal components. Next up, the second condition was what? Summation of what? Vertical components. From here now, listen. We said for this one here, consider upward force to be what? Positive and downward to be what? Negative. In this case, check the diagram here. Which force is acting in this manner? I have just what? 1, 2, 3. Right? Hence, in that case, we said any force going upward is what? Positive. Any force going down is what? Negative. Let us first, which force should we start with? Of course, I can start with this RAY. So, hence, RAY here is going what? Upward. So, I'll have what? RAY. Just plus RAY because what? The positive sign will be there. Next up, let's do with this. Sorry, this one. First with this. Second one is what? This. RBY is what? Going upward. Is it positive or negative? Positive. That's what? Positive RBY. Next up, I can see a force, a point load there, a vertical force here coming down. And we said down is what? Negative. So I have what? Negative 20 is now equal to 0. Summation of V is all this. Equal to 0 is this. That's all. What are the next steps? Next step is what? Take this one here to the what? Other side. I'll have RAY positive RBY is equal to 20 kilonewton. Call this our first equation, or call it equation asterisk. Call it equation asterisk. Alright. When we discuss the concept of equilibrium, we mentioned 3 conditions. The first one is what? Horizontal components. Next up, vertical components. What's the last one? We said moment. The summation of what? Moment at any point must be what? 0. Hence, from this diagram now, for the third condition, taking moments at point A. Now listen. I have point A here, point B and point C. Always take moments at a point where you know that has what? To the action this way. Right? So in most cases, I can even take note at point B. I'll still arrive at the same answer. Right? So let's start with A. Now, taking moments is as if this is my own illustration of moments. We said moment from physics concept is simply what? Force times what? Perpendicular distance. That's all. Right? Force and distance. Now listen. I'm considering 2 things. Force and then distance. Alright. We said we're taking what? Moment at A. Moment at A here is obviously 0. Why? We just said anywhere you are taking moment from what? Always equal to 0. So since I'm taking moment at A, automatically A is what? 0. So everything there is 0. That's all. And how many only 2 things left? This man and this man are left. This man and what? This man are left. Now listen. Let's have this man here. If this man here move, listen. We said for this one, consider this. For this man here, consider this. For this, what should we consider? Consider that clockwise to the what? Positive, anti-clockwise to what? Negative, right? So consider clockwise to what? Positive, and anti-clockwise to what? Negative. Now, let's have this point below here. This man here is going to move to meet point A. Since we are taking movement at A, all the remaining forces will move to A. Hence, let's start with this man here. If this man moves to A, it's moving in one sense. Is it clockwise or anti-clockwise? This is what? Clockwise sense. Hence, I will have what? I will have 20 multiplied by 20 is the what? Force that we just said here. Multiplied by from here to here. It's only from here to here, which is what? 5 by 5. I have this plus into. Consider second force. This man here will move in this manner. This manner is what? Is it clockwise or anti-clockwise? Obviously, anti-clockwise. That's what? Negative. Negative. Which force do we consider? RBY. That's RBY. Multiplied by which distance? From here down here. You said from here to here. Right? All forces are moving towards A. So from here down here is what? From here to here, which is what? 10. I have 10. I have this. Alright, 20 times 5 is what? I'll have 100. Then minus times plus is what? Minus what? 10 RB. Minus 10 RB is equal to 0. Is equal to 0. Right? So at this point, what do you do? I'll take minus 10 RB to the what? Other side. It becomes what? 100 is equal to 10 RB. Divided by 10 to get RB. Listen. RBY, I say RBY, so the same thing. 10 here and 10 here. This is up to this. So my RBY value is equal to 10 kilonewton. 10 kilonewton. This is how to draw. Sorry, this is how to calculate for RBY. So put RBY into equation aesthetics. What's my equation aesthetics? This is my equation aesthetics. So I have that RAY plus RBY is equal to 20. Hence, putting RBY as 10, I have RAY plus 10 is equal to 20. Get RA. Simply take this one, other side. I have that RAY is equal to 20 minus 10. Of course, RAY, by a mathematical approach, 20 minus 10 is what? Obviously 10 kilonewton. This is like the first tax. Calculate for what? Your reaction RAY and RBY. So my RAY is 10 and my RBY is 10. It makes sense. It simply means that this beam here is in a state of what? Equilibrium, disbalance. Right? This man here, I can illustrate something. If I say that beam can be drawn in this manner, let's say this is a person A holding this beam, person B carrying this beam. So what we just get now, we got that this man here is 10, this man here is 10 from here, RA is 10, RB is 10. Hence, let's say the power this man has is 10. This also has 10. But the force that's 20. Can't still withstand it. Of course, they can what? They can withstand it because since 10, 10 plus 10, because what then? 20. With this 20 shear force calculation, when it comes to shear force calculation, note two things. Number one, Note number one, if you are taking readings from the left hand side, let upward force positive and downward force be what? Negative. Note number two, if you are taking readings from the right hand side, upward force becomes negative. This becomes what? Positive. Right hand side. So note that when it comes to shear calculation, note two things. Number one, if I'm taking readings from my what? Alright, we said for shear force, note two things. Number one, whenever you're taking readings from left hand side, ensure that upward force is positive, downward force is what? Negative. We also said note two is that whenever I'm taking readings from right hand side, ensure two things. Number one is what? Ensure that upward force is what? Negative, down is what? Positive, right? So note that for left, I am still dealing with normal procedure. For upward force and downward force, this is normal procedure, right? What we use here, right? Normal procedure. But for right hand side, it has changed. What changed? You just interpret their sign. This becomes negative, not positive. Now, for my shear force here, I have three labeled parts. I have A, C, and B. A, C, and B. Those labeled parts, write them out. I have A, I have C, and B. In this manner, your first task. Next up, what's next? What do you do? We said, listen, no, for shear force, it's not left to us to choose which direction. But for me, I would like to use left hand side. Why? Because I am already familiar with upward force what? Positive and downward negative. So I'm familiar with this. Right? So I'm going to go for what? Left hand side. So I'm taking my own readings from what? Left hand side. So upward is what? Positive. Down is what? Negative. If that is true, hence at point A, what is my shear force at point A? That's the question. Alright. Coming down here, right? Coming down here, if I share section A, observe this. We said A is already what? R-A-Y already now, which is what? 10. Right? So if I share section A in this manner, I'm moving like this. So start section A this way. I have only what? Upward force here, which is this, going up. And we said for upward force for left hand side is what? Positive. So I have what? 10 kilonewton as my first value there. Listen, your first start section A. Which force? Now we're moving like this. Hence, if you section A, which force are you seeing here? I'm seeing only what? A upward force, which is this, which is R-A-Y. R-A-Y, question is that, is it facing up or down? Obviously, facing up. And we said, for left hand side readings, if a force is facing up, what do? Take it as what? Positive. Hence, I have what? Positive 10 kilonewton. Next up, please listen. For B, look up. For C, repeat this man down before you start anything. Repeat this man down, I have 10 here. For shear force, listen. For shear force, your first value here. After getting your first value here, before you go to the next one, repeat that value down here first before you continue. Alright, at section C now. If no, we're moving in this manner. If I ignore section A and not section A, if I proceed to section C, right? Section C is having a force here coming downward, which is what? 20. And force coming downward is what? Negative. So what? minus 20 here, which is what? Minus 10 kilonewton. Note this place, please. So for B, what will I put down first? The answer here will come down here first. Minus 10. Next up, for B, if I share section B, right? Section B, at this point, right? If I share section B, for section B, I have what? Just a force going upward here. Upward, and upward is what? Positive, which is what? RDY is what? RDY is obviously 10. That becomes plus 10, which is what? 0. Please, not put 0 to the ratio. There's nothing like 0 to the ratio, please. So, 0 does not have assignment, please. So I have 0 there. Now listen. For shear force, note two things. Number one, note this man. This one, we just discussed. Number two is that your first calculation here, any answer you have there, put it down first before you consider that other section. Now, after considering that other section here, as we have here, this answer you have here, drop it down here before considering the next section. I have this. Note two is that for shear force, you might not start with what? 0. But shear force always ends with 0. Please know that. Shear force, you might not start with what? 0. But ends with 0. Shear force always ends with 0. Please. Any calculation you are doing, and your shear force you have a value there is wrong, please. Shear force must be what? Always equal to 0. In some cases, the answer here might be 0.25. Sorry, 0.015. It's still 0. Approximately it's still 0. So your answer must be what? Must be equal to 0. Alright, let's do bending moment calculation, please. Bending moment calculation. Alright, bending moment calculation. We said for that being we just finish. We have three sections there, A, C, D. Put them down here. I'll have A, C, and B. For shear force, we do repeat value. What again? Anything I have here, I'll put it down here before I consider this section. Anything I have here, I'll put it down here before I what? Consider this section. But for bending moment, it is not like that. And when it comes to bending moment, note two things too. Note that number one, note that if I'm taking readings from my left hand side, clockwise is positive, anti-clockwise is negative. Left hand side. Alright, we just said that note number one is that if I'm taking this from what? Left hand side, clockwise should be positive, and clockwise should be what? Negative, as we know. But if I'm taking readings from what? Right hand side, ensure that clockwise is negative, anti-clockwise is what? Positive. Ensure this, please. This is note number two. Note number two. So note this, please. Note the difference between this man and this man when it comes to bending moment calculation and what? Shear force calculation. Alright. For section A, listen please. I'm okay with what? Taking this from what? Left hand side, please. I won't take this from what? My left hand side. for this one, I use what? Left hand side too. Obviously, for this man too, I will also use left hand side because I'm familiar with this man here. Clockwise positive, this one was negative. So let's go to the left hand side. Alright, in that case, listen. For section A, the diagram was something of this nature. Something of this nature. RBY, which is 10 kilonewton. Yes, RBY, which is what? Also 10 kilonewton. A force is here of 20 kilonewton. Right? From here to here, to this point, is given as 5 meter and 5 meters. All here B, all here B, all here C. Do the half initially. Right? So, let's start with A. If I take moment at section A, of course, section A becomes what? 0. From what we know, that anywhere you take moment from, so this is what? 0. So, if I start with A, if I take moment at A, of course, A is 0. Alright, if I done for A. For C, if I take moment at C, of course, C is also 0. But I'm moving what? Left hand side in this manner, right? Hence, if I take moment at C, here becomes 0. Which force am I seeing that's coming up to C? Listen, for A becomes 0, right? Because there's no force here, nothing is coming to A. Becomes 0, I have 0. For C, if C is 0, I still have a force coming like this, which is A. In this case, A will be alive, A will be existing. A is no more 0 because what? I'm considering another section, C. C becomes 0, A is not 0 again. So when A moves to C, A will move what? In this manner. This manner is called what? A what? A clockwise direction. So this is 10, like RA is 10. That becomes 10 times from here to this point here is obviously 5. 10 times 5. That's what? 50 kilonewton meter. Alright, when it comes to bend moment, SI is what? Kilonewton meter. When it comes to shear force, is what? Just kilonewton. Alright, for my point B, also similar, the same thing. For point B, if I take moment as point B, of course, point B is what? 0. It's off. It's 0. Now, if B is 0, I have two forces that should come to B. Now, if RA1 is 10, comes to B, that becomes RAY, that's 10 times what? Times 10. Let's get 10. That becomes 10 times 10. 10 times 10. Why? Because RA is moving what? In a clockwise manner to B. Because we're taking moment at B now. Right? So in that case, I have this man moving down here. In the distance of what? 5. 5 divided with 10. So I have 10 here. Next up, I'm going with A. C must go to B. If C goes to B in this manner, what direction is this? This is what? Anti-clockwise direction. That's what? Negative. That becomes minus. This is what? 20. From here to here is what? 5. 20 times 5. I have 20 times 5. Of course, I will have that 10 times 10 is what? 100 minus still 100. Final answer is equal to 0. Note that, listen please. Note that when it comes to bending moment always starts with 0 and ends with 0. Shear force do not start with 0 but always end with 0. Bending moment starts with 0 and end with 0. So this is how to calculate for shear force and bending moment diagram. Calculation per se. So let's draw out the diagram for the shear force and bending moment. In our next class, we're going to look at much more complex cases. For this one that we did now, just do a point load, right? That's the simplest way. That's an exam. Nobody can ask you for point load in exam. You'll be seeing, they'll be combining point load and UDA together for you to draw the shape of the moment. So after this class, in a beam together. We're also looking at point load, UDL, UVL in a beam. Right? So this is just a cake. Can't expect this in exam, please. Just know how it works. Know how it works. From this to all of this. So let's do our diagram. For my diagram, listen, to draw out your shear force and bending moment diagram, what do you need to do? Repeat your given question. I am given that I have a ring in this format. Repeat your question, please. I have this man here. If you recall, check your notes. You see this? I have this man. Right? Of course, I have a point load at the center of what? 20 kilonewton, no problem. We just said from here to here, from the question, is obviously 5 meter. From here to here is similarly 5 meter. Right? We said call here, section A, call here, section B, and finally section C. Now listen, this was my question. How did I draw the shear force? Your first task is what? Take A down this way. Right? Take section C down this way. And also take section B down this way. I have this. Next up, I'll take this one this way. 0.0. Upward is positive, down is negative. Agreed, no stress. Up is positive, down is negative. Now, this is for my shear force, please. Shear force diagram, please. Shear force diagram. Right? I have my shear diagram here. Now, listen. At section, this is for section A, for C and B. Question. At section A, what is my shear force? Of course, at section A, for my shear force calculation, A is for 10. So let's assume that this part here is for my 10, right? 10 kilonewton. At section C, here, what is shear force at C? Minus 10. Let's assume that minus 10 is somewhere down here. Minus 10. Finally, at section B, what shear force, please? 0. So here's my point 0 here. I have on 0. Hence, for point load, how do you draw the shear force? Your task is what? Connect them in this manner. Sorry. Down this way. Down here. Right? This is minus 10. Down here and this. This is how to draw the shear force of that man. This side is from negative. This is minus 10. This is minus 10. Negative, here is positive. So I have, you shade this way. You shade it this way. And shear force. This manner. Right? So this is our diagram for the shear force of this beam. Right? So next up, our next task says you draw the bending moment of this man. Of this question here. So to draw the bending moment is quite simple. Just draw a line this way. For my bending moment, listen. I'm not having negative sign. Just 0, 50, and 0. That's all. Hence, alright. Bending moment, of course, I'm not having negative sign here. Hence, I don't want to put this down here. Just come down here and draw a line this way. This is 0, 0. Check. Bending moment at section A is what then? 0. At section A is 0. Hence, I will aesthetic A this way. At section C, what the bending moment is? 50. Right? Check. 50. So let's say this is point 50 here. This is 50. Lastly, finally, at section B, check. I'm having 0. So this is 0. So for my bending moment, I will draw them what? Incline this way. I will draw it what? This incline. For point load, this incline in this manner. So I have bend moment diagram for this given question, right? So expect our next class on much more complex example on how to draw shear force and